Let's figure out the position equation for an object that is experiencing the resistive force as its net force. Continuing on with the situation of a bullet being shot into a gel block or a box being kicked across a frictionless floor. So far we've kind of introduced this model. We've looked at the force diagram, seen that the net force is equal to the resistive force. We've gone through some mathematics to get an equation for velocity as a function of time. And then we got acceleration as a function of time. So now we need to get position as a function of time. This one's a little bit more difficult. So I'm going to rewrite our equation here, v naught e to the negative k over mt. Let's make sure I'm correct. Good. So now how do we get to position? So change in position is equal to the integral of v dt. So now we have to integrate. And this is why we did this one second, because integration is usually more difficult than differentiation. But it's not that bad. Because again, the fact this is an exponential function makes things pretty easy. And you can just think about this in terms of differentiation by reverse engineering it. So if we are going to, so by the way, I've got delta x here, not x. I don't have position here. I have change in position or displacement. What we're going to do is we're just going to set x naught equal to 0. And what that's going to imply is that because delta x is equal to x minus x naught, that's going to mean that delta x is equal to x, because x minus 0 is x. So I'm going to start just writing x for that one. So x is going to be equal to the integral of v naught e to the negative k over mt dt. And again, v naught is a constant, so I'm going to move that out of the integral because I just like to move constants out of integrals. And we just take the integral of negative, e to the power of negative k over m times t. Of course, the integration or the integral of an exponential is just the exponential again, with a slight modification in this case because we have a function within a function. So you could use u substitution to do this, but I prefer to just kind of reverse engineer to figure out what I need to multiply by in front, which is really what u substitution is anyway. 6 of one, half a dozen of the other. So we get v naught e to the negative k over mt. Now we need to multiply by something to make this work. So what we want is something where when we take the derivative of it, we're going to get back to this. So when we take the derivative of this, we're going to bring down a negative k over m. So we need to cancel out that negative k over m. What would do that? A negative m over k. That would do that. And of course, plus c. So now we're going to have, just rewriting this a little bit because this is hideous, we're going to have negative v naught m over k e to the negative k over mt plus c. And that's all equal to x. So now what we need to do is figure out what c is. Well, we said that the initial position was 0. So at time t equals 0, our position will be 0. It's going to be equal to negative v naught m over k. This is going to become e to the 0, which is just 1. So I can ignore that, plus c. Right. Multiplying 1 times this doesn't do anything. So now, well, I can just move this to the other side. I'm going to get c is equal to, not negative anymore, v naught m over k. So then I can plug that back in there, and I get x as a function of time is equal to negative v naught m over k e to the negative k over m t. Notice how those switch. Plus v naught m over k. That looks kind of ugly for two reasons. One, I've got a negative dangling in front. I don't know about you, but I don't like that. Two, I've got a V naught M over K and a V naught M over K in two different terms. So what I'm going to do is swap the order of these two so the negative's not dangling in front, and I'm going to pull out a V naught M over K. So V naught M over K times, well, if I pull a V naught M over K out of V naught M over K, I'm just left with 1. Minus, if I pull a V naught M over K out of this, then I'm going to be just left with that, e to the negative K over mt. And so this then is a much nicer looking form of our function for position as a function of time. So does this one make sense? Well, so this is an exponential decay again. And this kind of graph, what this kind of graph looks like is something a little bit like this. Basic shape is going to be, if this is x, this is t, this would be V naught M over K, this constant in front, and then we're starting from x equals 0, and we're going to do this, and we're going to exponentially, or rather asymptotically approach that value over time. So this thing in front tells us how far this object is going to go before it stops. And if it was a bullet, how far into the gel block it's going to travel. If it is the box, how far it's going to slide on the frictionless surface after you kick it. So that's what this is going to be. So you could call that maybe d for distance it's going to travel. 1 minus e to negative k over mt. This form will come back when we look at something experiencing, I don't want to phrase it that way, something falling in a gravitational field with drag. I was going to call it free fall, but it's not technically free fall if there's drag. So we're going to see this basic equation form come up again. If you graph this, once again, take V naught to be 10, take M and K to be 1 or whatever you want. You can take V naught to be whatever you want as well. It doesn't have to be 10. It could be 50. It could be 3. And then plug this into a calculator and you will get this graph. Just to prove it to you, let's take a look. So V naught was 10 times, I don't need to use parentheses for that, times, well, 1 over 1 is just 1, so we don't need that at all. Parenthesis 1 minus e to the negative, 1 over 1 is just 1, x. And if we graph that, we get, oh my goodness, 10 times 1 over 1 is 10. So this thing that was kicked at a speed of 10 meters per second is going to happen to travel a distance of 10 meters before it stops. And look at that. That's the value. It's asymptotically, its position is asymptotically approaching 10 meters. Perfect. You may have also seen this mathematical form if you have taken a biology class and talked about carrying capacity of an ecosystem for a certain type of animal or plant or something like that. There are several applications of this particular equation. Now, what's the explanation for why this makes sense? Well, as t gets bigger, and this is maybe something I should have written out in past videos, the limit as t approaches infinity of e to the negative k over mt is going to be equal to 0. And that's what exponential decay means. So this term will decrease to 0, which means 1 minus 0 is 1. So that is why this is the final value, or the total distance this thing is going to travel, because as t gets very large, this term effectively becomes useless. It's just multiplying by 1. And when t is small, well, this term is going to be positive, and it's going to actually affect the outcome. So 1 minus some positive number that is less than 1 is going to be a smaller number than 1. Therefore, you multiply a number that's smaller than 1 by the total distance you're going to travel, and you're going to get a value that's less than the total distance you're going to travel, which makes sense. because you haven't gotten there yet. You haven't had enough time. Now, I mentioned that this is less than 1. How do I know that? Well, because if I just look at this function here, an exponential function without a coefficient in front of it always crosses the vertical axis at a value of 1, whether it's exponential growth or exponential decay. It will cross at this value of 1 there. The way you change where that crosses is by adding a coefficient in front of it. All right, I hope that clarifies that process. Next time, we'll take a look at drag for something that would otherwise be experiencing free fall.